Okay, so these videos are looking at examples of finding the derivative of a function and then using it to find slope and tangent and rates of change using the limit of the quotient, right? Because that's what it is. So you really should have, before you start my videos here, you really should watch the ones on my lab that explain where this limit comes from, this limit of the difference quotient, why it's important. It's important that you know that. I am just going to go over how to simplify it because that's the hard part of these. All right, so make sure you go and watch the MyLab videos on 1.4 that explain where this comes from. And so in these videos, I'm just going to practice the different types that you'll have to do. A quadratic type, a rational type, and a cubic type. There are linear types, but the book does those, and those are really simple. All right, so I'm just going to hit the harder types. All right, so the first video, is the quadratic type. So find the derivative of a quadratic function by solving the limits as h approaches 0 of the difference quotient, of the average rate of change. This finds instantaneous rate of change. That's what it finds, slope of the tangent line. So again, make sure you watch those other videos so you understand why we're using this. We're just going to now practice doing it. All right, use proper notation. So if on the show your work quiz and on the exam, if you don't use proper notation and show your steps, you'll lose points. Right, so do what I do. Right, do what I do. All right, so the first example is I want to find my derivative function, which is f prime of x, using the limit as h approaches 0. And you do have to put that limit out. The difference quotient is an average rate of change. When I put the limit of h approaching 0, it becomes the instantaneous rate of change. So that limit is very important. It changes the meaning. So if you don't have it, you're not finding the derivative. It's not the correct equal to, right? It's incorrect. It's a false statement. So you have to have the limit out front. And then you plug it in and simplify. All right, so the first step is to plug in the x plus h. So 3 times x plus h squared minus x plus h plus 5. So there's the first part, the x plus h, f of x plus h, minus parentheses f of x, which is 3x squared minus x plus 5. Make sure you put parentheses because you have to remember to distribute that negative. Divide by h. You have to include the divide by h because that's, again, part of the expression. It's like writing correct sentences in English. If you don't write the correct steps and notations, you're writing false statement. That's what the derivative equals. If you don't write it out exactly like that, it's not the derivative anymore. If you don't have the limit as h approaches 0, you don't have an instantaneous rate of change. You don't have the derivative. You have an average. We don't want average. We want instantaneous. We want slope of the tangent. All right, so that's the notation, proper notation that you have to use. And then the simplification, you have to show each step you're going to write an equal to sign. So you have to have the proper notation in each step so the equal sign is not false. Again, just like writing a paper, you have to have proper punctuation, capitalization, and sentence structure. Same thing here. All right, so there's going to be 3 things I'm going to do at once. The first thing I'm going to do is simplify the x plus h squared. I'm going to distribute the negative here, and I'm going to distribute the negative there. All right, so in my next step, the derivative is equal to, so you write an equal to outside the limit, equals the limit as h approaches 0 of, so make sure that's the notation, the equal to. For some reason, students want to put the equal to inside the limit. You don't want to do that. That's the limit of the difference quotient. So the difference quotient's inside the limit. Equal to is outside the limit. All right, so it's the limit as h approaches 0 of the average rate of change, which I'm simplifying. So 3 times, when I multiply that out, remember that comes out to x squared plus 2xh plus h squared when that multiplies out. Distribute the negative, so that's negative x minus h. There's a plus 5, and then this is going to give me negative 3x squared plus an x minus a 5, because I'm distributing it, right? This is, the second part where students mess up because they forget to distribute this negative. Negative is going to give me a positive x, and then a negative 5. Still divide by h. You have to write the divide by h just like you have to write the limit. Otherwise, it's a false statement. All right, next equal sign. Limit as h approaches 0 of. All right, my next simplification. Well, I've got to distribute my 3. This negative x cancels with that positive x. This 5 cancels with that 5, and that's it. That's all I can do. And so we get 3x squared plus 6x times h, 3h squared minus 3x squared all over h. All right, now the 3x squared cancels with the negative 3x. So I've got to where all my remaining expressions have h's in it. And so, and I left off an h. I missed that h there. So, right, I missed this guy. All right, so I should have 3 expressions with h. And so what I'm going to go ahead and, so I'm sort of showing you the bare minimum. If you need to take these step by step, take them step by step. In my next line, I'm going to go ahead and rewrite this as a split fraction, right? So this is gone, this is gone. And so instead of divide by h, the whole thing, I'm going to do it individually. So I'm going to take 6xh divided by h plus 3h squared divided by h minus h divided by h. And this is a little different than what I did in my notes. I did the factor method in my notes. So again, either way is fine. I wanted to show you both. I actually think this is the easier one, but the factor method is also perfectly fine. So that's the one I use when I have my completed notes. All right, limit h approaches 0 of the reduced form. So this reduces to 6x. This reduces to 3 and 1h, and this reduces to negative 1. All right, that's the goal, right? I want to get rid of the divide by h because my next step is going to solve the limit, right? We solve the limit by inputting h equals 0. You take the 0 and you plug it in, right? Can't plug it in before that because I get division by 0. All right, this again is a special rule that we are allowed to use to solve the limits. All right, so once we get rid of the divide by h, I can now plug 0 in for h. All right, when I do that, key word here is I've solved the limit. Ergo, my next line has no limit in it. I've solved it. The solved limit is this zeroes away. So I'm left with a 6 times x, that's gone, and a negative 1. Notice on that line there's no limit. That is what the derivative is equal to. And then I basically bring this guy all the way down. And there is my derivative. That's the derivative of the original f of x, which remember is the instantaneous rate of change at any moment, at any x value, which means I can find my slopes and I can find my slope of my tangent lines, right? That's what we're going to do in the next expression. Use the derivative function, so that function I found up there, to find the slope and the equation of the tangent line at a specific... So again, there are infinitely many points I could have picked. I picked negative 1, 9. All right, so that's the one moment I'm interested in. We're going to graph it in a little bit just to show you where it shows up. So I'm going to use the derivative, right? That's what the derivative is for. It's to find the instant rate of change, which is my slope of my function. And then I can find tangent lines that have that same slope, same speed and direction. All right, so we're going to want to find y equals mx plus b. All right, find my equation of my line and my slope. We find the slope is my derivative, right? The derivative finds any slope, right? That'll give me any slope. Well, I picked one. I want to find the one we're looking for instead of any slope. We want to find it at the given point, which means at x equals negative 1, right? That's the x value. And so the slope I'm looking for is I'm going to take my derivative and plug negative 1. I could have picked any value. I picked negative 1. All right, so I'm going to take negative 1, plug it in my derivative. So 6 times negative 1 minus 1. And so the slope I'm interested in is negative, which means my original function, my quadratic, is decreasing at a speed of 7 units of y per unit of x. That's decreasing because it's negative. All right, so there's the first piece. The slope of the tangent line is -7. All right, so I've got my slope. Now I need the equation. Well, that's where I'm going to use this point. All right, I have an x value of -1, a y value of 9. Right, that's the function value. F of -1 equals 9. Plug those in. So 9 is the y value. Slope was -7. X was -1. And solve for b. Oops, I don't know why I changed that to 8. Should have been 7. So it should be -7 times -1 is +7. And so when I subtract 7 for both sides, it should come out of b of 2. All right, so my equation of my tangent line is y equals a slope of -7 times x and a y-intercept of +2. And there's my equation of the tangent line to my original f of x at the moment, at the single point, 1, -1, 9. All right, at that one moment, that's its tangent line. So it's decreasing at a rate of -7 units per change in x. All right, now to look at it, what's happening. So again, you should always understand the visual of it, right? So understand what's happening. And you can use your calculator. So y1 on your calculator would represent the function f of x, which was 3x squared minus x plus 5. y2 would represent your tangent line, which was -7x plus 2. You might want to make your window a little bigger because remember a point of tangency where a tangent line hits is at -1, 9. So what I will probably change my window to when I go to use my calculator is I'll probably change my y maximum. I'll probably raise it to 15. I'll leave all the rest of them 10s. The standard window would be, so if you have a standard, if you click standard window first, it should be max and min should be 10 and -10 for everything. I would just change my y to 15 so that you can see everything that's going on. All right, and then just sketch the graph. So the parabola opens up. It goes to the point when I plug in 0, it's at 5, and I know I need to go up to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. -1, +1. So 1, 2, 3, 4, 5. So it goes through the vertexes at somewhere, again, that's what the y-intercept, not the vertex. The y-intercept is at 0, 5. All right, -1, 9. Puts me about right there. There's my -1, 9. And then again, the parabola shape. And there's my f of x. And there's my point of tangency. And then I'm going to switch colors to draw my line. So the other point that I'm going to do, right, in order to draw my line, I need 2 points. I've got this point that it shares on my function f of x, and then I'm going to use the y-intercept. The y-intercept is 0, 2. And so there's the 0, 2 y-intercept, and then I'm going to connect it up. And it should just touch the curve. Make sure I can draw a little better than that. So it should just touch the curve there, not cross it. And again, just touch it and go off. And so the red line is my y equals -7x plus 2. The 2 points that I used to graph the red line was the intercept 0, 2, and then the point where it touched the f of x. And so again, slope, it was -7, so what that means is f of x is decreasing. And if you look at the graph, it is. And I know exactly how much it's decreasing. It's decreasing by 7 units of y per change in x. That's exactly what it means. It means I'm moving down, negative direction, by 7 units of whatever my function y represents per change in x at that moment. Now, if I picked a different moment, I would have a different value, right? If I picked the point over here, it would be an increasing moment, right? If I picked the point over here, it would be increasing even faster. Here would be decreasing, and so on. All right, and so that's the specific moment that I picked. All right, we'll stop there. We'll do the next example, which I believe is the rational function in the next video, and then end it on the cubic.